The prediction of the molecular geometry of phosphorus pentachloride using the VSEPR, valence shell electron pair repulsion theory. We will first try to draw the Lewis structure. Phosphorus is the central atom. Phosphorus is found in the 5th group and 3rd period of the periodic table. It has got 5 valence electrons that can be used for covalent bond formation. And also very important, phosphorus has got d orbitals. Having the d orbitals will imply that phosphorus can form the expanded octet. The terminal atoms are the chlorine atoms. Chlorine is found in the 7th group and 3rd period of the periodic table. It has got 7 valence electrons for covalent bond formation. Being the terminal atom, it will only form single bonds. Central atom phosphorus, 5 valence electrons. 5 chlorine atoms. We've got a central atom A bonded to 5 terminal atoms. No lone pairs on the central atom. Therefore, the electron pair geometry will be the same as the molecular geometry AB5. For an electron pair geometry AB5, we predict a trigonal bipyramidal molecular geometry. The trigonal bipyramidal structure has got an axial and an equatorial position. We will use Cooper or Cowper structures to draw the molecular geometry. We've got a central atom phosphorus. In the axial positions, we've got 2 chlorine atoms. In the equatorial position, we have got 3 chlorine atoms. We can introduce the lone electrons on the terminal atoms. These lone electrons will not influence the molecular geometry. Prediction of bond angles. We have got perfect bond angles of 120 degrees. For the chlorine axial, phosphorus chlorine axial, we expect a bond angle of 180 degrees. The axial bond length will be a bit longer than the equatorial bond length, and the measured bond lengths are 214 picometers for the chlorine axial phosphorus bond, and it will be 202 picometers for the equatorial chlorine phosphorus bond. When we look at the molecular geometry, we have got a trigonal bipyramidal structure. The molecular geometry will depend on the positions of the nuclei. We go from chlorine nucleus, phosphorus, chlorine, 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 chlorine nucleus. Only distortions will be bond length change. The only distortions will be the different bond lengths. The phosphorus chlorine axial a bit longer than the phosphorus chlorine equatorial. The prediction of the molecular geometry of chloral trifluoride using the VSEPR theory, valence shell electron pair repulsion theory, and we draw the Lewis structure first. Chlorine is the central atom. Chlorine is found in the 7th group and 3rd period of the periodic table. It has got 7 valence electrons that can be used in covalent bond formation. Very important though, the d orbitals of chlorine. Chlorine can form the expanded octet using the d orbitals. It can accommodate therefore more than 8 electrons around the nucleus. Chlorine, being the central atom, can form either single or double bonds. Oxygen is found in the 6th group and 2nd period of the periodic table. It has got 6 valence electrons and can form covalent bonds by either forming double bonds or single bonds. The fluorine atom is found in the 7th group and 2nd period of the periodic table. It has got 7 valence electrons and will form single bonds, being the terminal atom. Central atom chlorine, 7 valence electrons. Fluorine, 7 valence electrons. Oxygen, 6 valence electrons. That bond formation between the chlorine and oxygen atom can take place by the formation of a dative covalent or a coordinate covalent bond, where the chlorine atom will donate 2 electrons to an open orbital around the oxygen atom. In such a case, the oxygen atom will form an electron octet. When the central atom has got d orbitals and we want to predict a molecular geometry that will compare better with the geometry measured in the laboratory, we change these dative covalent bonds or coordinate covalent bonds to double bonds. So that for a better Lewis structure, we suggest that the chlorine atom will form a double bond to this oxygen. The oxygen will still have its electron octet. It will form a double bond to the other oxygen, and then it will form the single bonds to the fluorine atoms. The molecular geometry, we have got a central atom A bonded to 5 terminal atoms. This will be the same as the electron pair geometry AB5 because we haven't got any lone pairs around the central atom. The electron pair geometry AB5 will predict a trigonal bipyramidal molecular geometry. We have got a so-called axial and an equatorial position. We make use of Cooper or Cowper structures to draw the molecular geometry. We've got a central atom chlorine. The more electronegative fluorine atoms will be placed in the axial positions. The 3rd fluorine atom will then of course be in the equatorial position. The double bonds are always placed in the equatorial position. We predict then a structure where we have got slight distortion between the 2 double bonds. We expect this bond angle to be a bit larger than the perfect expected 120 degrees. And we expect this bond angle to be a bit smaller than the perfect 120 degrees. The bond angle, fluorine axial, chlorine axial, will be more or less 180 degrees. So that if we look at the molecular geometry, it is important to realize that molecular geometry will depend on the positions of atomic nuclei in 3-dimensional space. This is the chlorine atom. In the axial positions, the 2 fluorine, the 2 more electronegative atoms. Of course, there's a 3rd fluorine atom. Then the 2 oxygen atoms. And there will be a slight distortion because of the presence of a double bond. The structure then, trigonal bipyramidal. The prediction of the molecular geometry of sulfur tetrafluoride using the Vesper theory, valence shell electron pair repulsion theory, and we draw the Lewis structure first. Sulfur is the central atom. Sulfur is found in the 6th group and 3rd period of the periodic table. It has got 6 valence electrons for bond formation. Very important though, sulfur has got d orbitals. That will imply the formation of an expanded octet where necessary. The fluorine atom is found in the 7th group and 2nd period of the periodic table. It has got 7 valence electrons for covalent bond formation. Fluorine is a terminal atom and will only form single bonds. Sulfur having 6 valence electrons, and we've got 4 fluorine atoms, 7 valence electrons. For the molecular geometry, we have got a central atom A bonded to 4 terminal atoms having 1 lone pair. Electron pair geometry A, B, 4 plus 1 make 5, and that will describe a trigonal bipyramidal molecular geometry. In the trigonal bipyramidal molecular geometry, we expect 2 positions, the so-called axial position and a so-called equatorial position. In the equatorial positions, we expect the lone pair, and we expect the bond lengths to be shorter than in the axial positions. We draw Cooper or Cowper structures for the molecular geometry. We have got a central atom sulfur, 2 fluorine atoms in the axial positions, 2 fluorine atoms in the equatorial position. This fluorine atom pointing out of the paper towards the reader, this fluorine atom going to the back of the paper, and the lone pair here. For the perfect trigonal bipyramidal structure, a bond angle of 120 degrees can be expected. In this example, though, we have got not the trigonal bipyramidal structure, but a distorted structure where we've got a lone pair in the position of one of the nuclei. So that we have got atomic nucleus fluorine, atomic nucleus sulfur, atomic nucleus fluorine, atomic nucleus fluorine, atomic nucleus fluorine, and that will describe the so-called seesaw molecular geometry. We expect this bond angle to be smaller than 120 degrees. The volume of a lone pair is larger than the volume of any double bond, and that is larger than the volume of a single bond. So the repulsion of the charge of the lone pair will cause these single bonds to move a bit closer together. And in actual fact, we find that the bond angle is 101.6 degrees. The repulsion of this lone electron pair will also influence the bond angle of the fluorine axial, sulfur fluorine axial positions. Instead of the perfect 180 degrees that is expected, we find that this bond angle is larger than 180 degrees, but 187 degrees, making, of course, the bond angle from this side 173 degrees. The fluorine axial sulfur bond length is measured to be 164.6 picometers, and the fluorine equatorial sulfur bond length is measured to be 154 picometers. It is important to realize when looking at the molecular geometry that for the electron pair geometry we have replaced one nucleus, atomic nucleus, with a lone pair, the lone pair in the equatorial position. The molecular geometry will depend on the positions of the atomic nuclei in three-dimensional space. Fluorine axial, fluorine axial, fluorine equatorial, and the central atom sulfur. We describe the seesaw structure, and there will be distortions because of this lone pair in the molecule. The prediction of the molecular geometry of iodosyl trifluoride using the Vesper theory, valence shell electron pair repulsion theory, and we draw the Lewis structure first. Iodine is the central atom. Iodine is found in the 7th group and 5th period of the periodic table. Iodine has got 7 valence electrons that can be used in covalent bond formation. Being in the 5th period implies that iodine has got d orbitals and can form the so-called expanded octet and single or double bonds where necessary. The oxygen atom is found in the 6th group and 2nd period of the periodic table. It has got 6 valence electrons for covalent bond formation. Being a terminal atom, it can form either single or double bonds. The fluorine atom is found in the 7th group and 2nd period of the periodic table. It has got 7 valence electrons for covalent bond formation and will form only single bonds. Iodine with 7 valence electrons. We've got 3 fluorine atoms, and we'll form the normal electron octet around the fluorine atoms. 1 oxygen atom. We can suggest the formation of a dative covalent bond where the central atom iodine will donate 2 electrons to an open orbital around the oxygen atom. When the central atom has got d orbitals though, and we want to predict a molecular geometry that will compare better with the geometry measured in the laboratory, we change this dative covalent or coordinate covalent bond to a double bond. So a better suggestion for the Lewis structure will then be central atom iodine, double bond to the oxygen, and we have still got the electron octet around the oxygen. The 3 fluorine atoms will have electron octets. And we have got the lone pair on the central atom. Molecular geometry, central atom A, 4 terminal atoms, very important, the lone pair on the central atom. Electron pair geometry will be AB, 4 plus 1 will be 5. Electron pair geometry AB5 will predict a trigonal bipyramidal molecular geometry. In the trigonal bipyramidal molecular geometry, we have got a so-called axial position and a so-called equatorial position. The more electronegative atoms will always be found in the axial positions. The double bonds and lone pairs will be found in the equatorial position. For the perfect trigonal bipyramidal structure, we expect the equatorial bond angle to be the perfect 120 degrees and the actual central actual atom to be 180 degrees. We make use of Cooper or Cowper structures to draw the molecular geometry. The central atom iodine. More electronegative atoms will be placed in the actual positions. The lone pair will be placed in the equatorial position, and we've got a double bond oxygen and the single bond fluorine. We predict a distortion in the molecule, and we predict that the bond angle will be smaller than 120 degrees. In actual fact, this bond angle is measured in the laboratory to be 98 degrees. We predict the distortion of the actual fluorine central atom, actual fluorine, and we find that this bond angle is in actual fact 192 degrees. We expect different bond lengths in the axial and equatorial positions. In the axial position, we expect the iodine-fluorine axial bond length to be a bit longer, and this is measured as 183 picometers, while the iodine equatorial bond length is measured as 174 picometers. The molecular geometry will depend on the positions of the nuclei in three-dimensional space. Electron pair geometry will predict a trigonal bipyramidal structure, but we've got now an electron pair in the equatorial position. The molecular geometry then, fluorine axial, central atom, iodine, fluorine axial. Then we've got the oxygen atom in this position and another fluorine atom in that position in the equatorial positions. So that the molecular geometry then, the so-called seesaw structure. Distortions because of this lone pair found in the equatorial position. The prediction of the molecular geometry of chlorine trifluoride using the VSEPR theory, valence shell electron pair repulsion theory, and we draw the Lewis structure first. Chlorine is the central atom. Chlorine is found in the 7th group and 3rd period of the periodic table. It has got therefore 7 valence electrons that can be used in covalent bond formation. Very important though is the fact that chlorine has got d orbitals and can form the expanded octet. Fluorine of course is found also in the 7th group, but in the 2nd period. Fluorine has also got 7 valence electrons for covalent bond formation. Fluorine though has not got any d orbitals and can only form the so-called electron octet. Chlorine with 7 valence electrons, 3 fluorine electrons. We see that we form electron octets around 3 fluorine atoms, and that the chlorine atom will have the so-called expanded octet. 1 pair there, 1 pair there, that's 4 electrons, and then 2, 4, 6, altogether 10 electrons around the central atom. Molecular geometry, we've got a central atom A, 3 terminal atoms, 2 lone pairs. Electron pair geometry A, B, 3 plus 2 makes 5. Electron pair geometry AB5. AB5 predicts a trigonal bipyramidal molecular geometry. Perfect bond angles of 120 degrees in the equatorial position. This position here in the center is called the so-called equatorial position. This position, the so-called axial position. For our molecule, we use Cooper or Cowper structures to draw our molecule. We've got a central atom, chlorine. The more electronegative atoms, but of course here we've got 3 fluorine atoms, but the fluorine atoms are always placed axial. The 3rd fluorine atom must be placed then equatorial. Lone pairs are always found in the equatorial position. This is called the so-called T structure, where we look at the positions of atomic nuclei in 3-dimensional space. Fluorine axial, chlorine central, fluorine axial, fluorine equatorial, so-called T structure. We expect bond angle distortions. Instead of a 90-degree angle, we expect bond angles to be smaller than 90 degrees. It is in actual fact measured as 87.5 degrees. The reason being, of course, the presence of the lone pairs. the volume of a lone pair will be larger than the volume of any double bonds or single bonds. We also expect the bond lengths not to be exactly similar. In the axial position, we find a bond length of 169.8 picometers, and in the equatorial position, we measure in the laboratory a bond length of 159.8 picometers. The electron pair geometry was trigonal bipyramidal. We have got two lone pairs though. The lone pairs are found in the equatorial positions. We can see then that we have got a so-called T structure where the molecular geometry depends on the presence of the nuclei, not on the presence of the lone pairs. The lone pairs will cause distortions, but the presence of the nuclei, atomic nuclei, fluorine axial, chlorine, fluorine axial, fluorine equatorial, the so-called T structure.